Hello and good morning or good afternoon to all our guests and speakers from around the world. My name is Shakil Akhtar and I am the Global Product and Business Development Manager for wear-resistant coatings working for Atotech. First, thank you very much to the TFSA for organizing this seminar and giving us the opportunity to present our latest developments at this forum. I will be presenting two sustainable plating processes today. The first is a trivalent hard chrome plating process, which is completely environmentally friendly in comparison to the existing hexavalent chrome, also referred to as chrome 6 based chemistries for plating functional chrome coatings. The second process I will discuss is a metal-free stabilized electroless nickel, which is a lead, cadmium, antimony, and bismuth-free process. So let's start. Atotech has been pioneering developments of environmentally friendly, responsible plating solutions for functional and decorative applications for decades. To keep in line with this tradition, we are proud to present our trivalent hard chrome process called blue chrome. The blue chrome is the first process of this type to be made available commercially for mass production in the market. The key driving force for developing a trivalent chrome process is the new environmental legislations being introduced in Europe by the REACH committee. The main requirements of the process from the onset of development was to offer the same deposit properties as the existing hexavalent chrome process currently used in the industry. These requirements being high wear resistance, low coefficient friction, high hardness, high corrosion, and chemical resistance. Hexavalent chrome plating is one of the most hazardous and dangerous processes in the field of electroplating. The reason for this, when we consider the different chemicals that constitute the process formulation. The bath is composed of some very hazardous substances such as chromic acid, which is considered as a very toxic and carcinogenic chemical amongst other hazards. Sulfuric acid, which is highly corrosive chemical, is used as a catalyst in the bath formulation. The process also uses lead anodes, which are converted to lead oxide and lead chromate during the plating process. The process uses wetting agents to reduce toxic fumes, and the chemistry used for this purpose is using inert PFOS and PFAS fluorosurfactants, which are also considered as hazardous substances. Now in the US and in Europe, there is a strong drive to get rid of these forever chemicals in order to avoid high concentration of these entering the freshwater resources. In slide 5, we can see how the hazardous nature of both processes compares. Basically, we are going from a CMR to a CMR-free process. CMR stands for carcinogenic, mutagenic, or toxic to reproduction. In 2017, due to the hazardous nature of chrome 6 substances, the REACH committee in the European Union proposed the deadline of 2024 for the ban of these chemicals. The proposal was accepted in principle by the European Parliament, and a decision on implementation of the legislation is now expected in the very near future. This means the hexavalent-based processes cannot be used beyond 2024, and exceptions can only be obtained by license. The major issue here is that the license fees are deliberately set at high levels to force non-critical applications to other types of more environmentally friendly processes. The license fee is expected to cost anything ranging from 50 to 100,000 euros. So let us look at how the blue chrome electrolyte differs from the hexavalent process. As mentioned earlier, the blue chrome trivalent process does not contain the hazardous chromic acid, lead and lead chromate, or the PFAS fluorinated surfactants. The chromium is added to the bath via the chromium-3 salts and operates at a much lower metal content of 15 to 30 gram per liter. The chrome-3 salts are much safer to handle and are more environmentally friendly compared to chromic acid. The pH of the process is less acidic, and to keep the chrome in solution under these conditions, complexants and buffering agents are added in the bath. The operating condition of the blue chrome in terms of cathode current density and temperature are comparable to hexavalent processes. As far as equipment requirements are concerned, due to the corrosive nature of hexavalent chrome processes, expensive PVDF tank material is usually recommended. However, the blue chrome process can be operated in tanks constructed from cheaper polypropylene materials. Blue chrome can be operated with graphite, platinized titanium, or mixed metal on titanium anodes. Thus, the elimination of toxic lead from the process with blue chrome. All other requirements, equipment requirements, are the same. In most cases, the existing hexavalent tanks can be cleansed thoroughly. They can be used with the blue chrome process. The additional requirement is that the blue chrome requires filtration of the bath as well. Slide 9 shows the plating speed of the process in that it's comparable to the leading Heath process under the same cathode current density conditions and is higher than the conventional hexavalent process. The bath life of the process is comparable to the industry standard hexavalent process. We have now operated the bath in our technical center to more than 900 ampere hours per liter to date. And results so far are still looking very good. In slide 12, we can see the pretreatment and plating sequence for both the processes. Due to the aggressive nature of the hexavalent process, it requires bare minimum of surface treatment prior to the chrome plating. The hexavalent bath is a good cleaner due to the highly oxidizing nature of the chromic acid. It also plates direct onto the steel surface. In comparison, the blue chrome, due to its mild chemical nature, requires the substrate to be thoroughly cleansed prior to plating the chrome deposit. Additionally, it requires nickel underlayer on the steel surface. Hence, the process sequence is longer compared to a standard hexavalent process. Let's take a look at the deposit properties in detail. Hard chrome coatings are typically cracked due to the change in the crystal structure which occurs immediately after forming. The initial deposit is a hydride of chromium, which is very stable and loses its hydrogen atoms quite quickly. The loss of the hydrogen forces a change in the structure from a hexagonal face-centered lattice to a body-centered cubic lattice. Crystal structure change results in a 15% shrinkage of the deposit, which leads to buildup of high stresses within the deposit. This stress forces the deposit to crack and thereby release the stress. The image on the top right-hand corner shows the surface of a typical chrome plated layer with a crazy paving like pattern of cracks. With the hexavalent process, the crack depth is usually 1 to 2 microns and can be seen in the etched cross-section of the heave process. During the plating, as the thickness increases, the first set of cracks that form get covered and new cracks form in different locations within the deposit. However, the blue chrome tends to form macro cracks, which have a tendency to penetrate all the way through to the deposit onto the base material surface, as seen in the image. As far as the blue chrome deposit appearance is concerned, it is very similar to that produced from hexavalent processes, i.e., it looks bright and shiny. It can be plated with very high thicknesses of up to 300 microns. In slide 15, we can see the macro cracks at a higher magnification. Negative consequence of these macro cracks is that the corrosion protection afforded by the deposit is reduced. However, we can counter this effect by the application of a nickel underlayer, which helps to overcome this deficiency and provide superior corrosion protection compared to hexavalent deposits, as we will see in the preceding slides. Semi-bright electrolytic nickel can be used as the underlayer. With the nickel underlayer, the chrome protection is superior to the industry standard hexavalent process HEAF 25 when the correct post-treatment conditions are used. In this graph, rods plated in blue chrome were baked and polished with different conditions, as can be seen. After polishing, the neutral salt spray results for blue chrome exceed HEAF 25. During our corrosion studies, it was established that blue chrome deposit is more inert compared to the hexavalent deposit in chloride-containing environments due to the inclusion of carbon within the coating. This carbon gives the blue chrome an advantage in the mining and marine applications. The two bigger pictures at the bottom of the slide show that chrome 6 develops white spots after 96 hours of exposure, whereas the blue chrome remains unchanged. These results have recently been confirmed in service on hydraulic bars plated with blue chrome and used in mining equipment in Poland. Blue chrome in this scenario lasted 1800 hours compared to chrome 6 plated bars, which only last for 1000 hours. So we get a factor of 1.8 increase in service life. Slide 18 shows the hardness data measured via a Vickers hardness machine with a diamond tip in the top right-hand corner. The as-plated blue chrome is slightly softer than HEAF 25, but heat treatment after plating increases the hardness to a similar range as HEAF 25. The post-grinding induces heat to the surface of the blue chrome deposit, and this results in an increase in the hardness. In slide 19, this shows the roughness measurements on the as-plated deposit and shows a higher value than hexavalent chrome, but after polishing and baking, comparable results can be achieved. It is clear from this study that the polishing and baking conditions needed to be optimized for a given application or in a given environment. The slide 20 shows the wear data for abrasive wear conditions using the Tabor abrader. Due to the slightly lower hardness, blue chrome deposit wear is slightly higher than the HEAF 25, but lower than a conventional process. We can state the benefits of the trivalent hard chrome as follows. Blue chrome is the first commercially available process in the marketplace. The blue chrome is a stable process and offers a long bath life. Blue chrome fulfills all the quality requirements of a hard chrome deposit, is a completely sustainable process. The second process I want to present today is our 11HP1050, which is a metal-free stabilized electroless nickel process. The key driving force for this process is the Atotech Green Development Roadmap. The first generation of processes were based on lead and cadmium stabilizers. The second generation were developed to comply with the ELV legislation and used alternatives which were toxic but less than the lead and cadmium. The third generation were based on mixed stabilizer systems using both metal and non-metal stabilizer systems. And finally, we have the fourth generation, which is our NICAM HP 1150, and this is completely metal-free stabilized and thus better for the environment. The 11HP 1050 process operates with a 6 gram per liter nickel content at a pH of 4.5 to 4.9. Temperature of the process lies between 86 and 90. And under these conditions, the plating rate of the process is in line with the existing processes at 8 to 12 microns per hour. The HP 1050 has a wide operating window and can operate with bath loadings ranging from 0.25 up to 2.5 square decimeters per liter. The electroless nickel is a chemical process for the deposition of the metal, and the deposition mechanism has to be controlled in order to avoid plating on unwanted surfaces such as the tank walls. Thus, bath stability is an important factor to ensure a trouble-free operation. Stability in the bath is controlled by the use of stabilizers. The bath stability of the HP 1050 is extremely good and is superior to the existing processes over the whole bath life. With lead stabilizers, the bath beaker stability test is in the range of 1 to 3 cycles. With HP 1050, we are able to achieve more than 3 cycles. The process was benchmarked against the high PEN standard bestseller currently in the market in terms of performance. The plating rate of the process over the bath life was comparable against the standard, which shows that the use of metal-free stabilizer has no influence on the plating rate. The process was operated throughout the bath life at similar bath loading and showed comparable results. No skip plating at low bath loading was observed from a new makeup, and good initiation with full coverage on copper substrates was obtained. Next, we take a look at the deposit properties. With the electroless nickel coatings, tensile stress is to be avoided. High stress can lead to cracking of the deposit when plating thick deposits. The HP 1050 process plates with a compressive stress from 0 to more than 6 metal turnovers. And this is in line with the current technologies. The HP 1050 is a high phosphorus electroless nickel process, and as such, the percent phosphorus content lies within the 10 to 12% range throughout the bath life. And this is comparable to metal stabilized systems. The resistance to acidic environments is a critical property of the phosphorus. A common method used in the industry is to assess this property is to use the nitric acid test. Upon immersion in concentrated nitric acid over a 30-second period, no discoloration of the deposit should be observed. HP 1050 passes this test over the whole bath life. Immersion up to 20 minutes also gives satisfactory results. The Fraxal test is used to determine the porosity level in the coating, and HP 1050 demonstrates excellent results with no pores over the bath life. Another important set of properties for electroless nickel coatings is the hardness and wear resistance. Electroless nickel coatings undergo structural changes when subjected to heat treatment. The as-plated deposit is amorphous in structure, and upon heating the deposit at 300 to 400 degrees centigrade, the deposit becomes crystalline. The crystalline structure has a high hardness compared to the amorphous structure as a result of deposit shrinkage. The evaluation of hardness shows comparable wear behavior and hardness against standard EN process with 7 to 12 milligram per thousand cycle for the heat-treated sample in a Tabor wear test, and hardnesses of 520 to 620 Vickers were measured via a Vickers hardness machine. A clear benefit of the HP 1050 over the standard process is observed when comparing the ductility of the deposit. The deposit produced from the HP 1050 is more ductile by up to 25%. And the benefit of this is that we do not find any cracks in the deposit when bent at a 180-degree angle over a 10 millimeter mandrel. The standard process shows cracks in the coating under these conditions. This ensures that when deposited on components which may encounter some deformation during assembly, the deposit will not crack. Cracking reduces the corrosion protection of the deposit. For assessing the corrosion protection, a few different methods are used, and we will see in the following slides. One such method is the Cadmium test. The Cadmium test involves the exposure of the deposit to corrosive sulfur dioxide gas over a defined period of time, and this cycle is repeated on several cycles. The discoloration of the deposit or any attack to the coating is an indication of failure of the deposit. The usual requirement is to pass 4 cycles with a 75 micron thick deposit. HP 1050 easily passes this test compared to standard EN, which shows discoloration after 4 cycles. The other type of corrosion tests are the neutral salt spray test, or referred to as NSS. This test is conducted with a neutral pH. A solution of sodium chloride at 5% concentration is used. The sodium chloride is aspirated in a chamber containing the test panels. The left-hand side panels show that Nikon HP 1050 has no corrosion spots after more than 1,000 hours in the neutral salt spray chamber with a 25 micron deposit thickness. The panels and data on the right-hand side show the results obtained with an acetic acid salt spray test, also referred to as AASS test. The AASS test solution contains acetic acid along with sodium chloride, and the test is more aggressive compared to the NSS. The results show that the corrosion behavior of HP 1050 is superior to the standard EN process. The normal requirement is to pass 96 hours on steel substrate, and more than 144 hours are achieved with the HP 1050 process. The 11 HP 1050 process is the most sustainable conventional electroless nickel process on the market. It is an ELV, Roche and WE compliant process. It uses no toxic substances like lead, cadmium, bismuth, antimony, EDTA, and boric acid. It offers technical benefits such as compressive stress and ductility and superior corrosion protection throughout the bath life. The process is economical to run as it offers 10 to 15% longer bath life, and deposit performance exceeds the standard process, thereby extending the life of the components in service. To finish, we can summarize both process inventions as follows. The blue chrome process is the first trivalent chrome process on the market. It fulfills all the requirements of the hard chrome deposit and requires and is a stable and offers a long bath life. It provides superior corrosion protection as compared to existing technology. It has already been used in industrial conditions. The 11 HP 1050 metal free stabilized is the most environmentally friendly conventional EN process on the market. It demonstrates high bath stability and long bath life. It offers superior corrosion protection and more ductile deposits compared to standard metal stabilized processes. It is also in industrial use. So on that note, I would like to take the opportunity to thank you all for participating in this seminar and patiently listening to this presentation. And I look forward to your questions. Thank you very much.